Good afternoon. Last tips for assignment, or actually the workshop questions B3 and B4. Maybe I give some tips on A1, A2. So what's the question? We have a function f, which is x, y, z plus z, subject to x squared plus y squared plus z less or equal than 6, and x, y, z are bigger than 0. Asked to see that there are two solution candidates and one has to determine the maximizer using the Kuhn-Tucker theory. So we need the KT Lagrangian, which is Lxy, is it z, and then lambda, L bar of course, which is z itself, xyz plus z, minus lambda times x squared plus y squared plus z minus 6 is 0. So that's step 1. Step 2 is we write down the KT relations. So that's x L bar dl dx. So that's x times yz. Yz minus 2 lambda x is 0. It's 1. Oh, it's 1. It's 1. We label them. Y times L bar dl dy. It's late on Saturday, so that's xz minus 2 lambda y is 0, that's 2, and then z dl by dz is z times xy plus 1 minus just 1 lambda is 0. 1 is 3, and then minus lambda dl by d lambda, which is the lambda times x squared plus y squared plus z minus 6 is 0. Then we need the dl dx, dl bar dx, which is yz minus 2 lambda x is less or equal to 0. L bar dy is xz minus 2 lambda y less or equal than 0, and L bar z is xy plus 1 minus lambda is less or equal than 0. We call that 5. Less than equal than 0, we call that 5. And then x bigger or equal than 0, y bigger or equal than 0, z bigger or equal than 0, and lambda bigger or equal than 0. We call that 6, not 7. 6. Minus lambda. So this is a useful relationship because we see that lambda is bigger or equal than 1 plus xy. That means that lambda is bigger than 1, so lambda is bigger than 0. So that means in this relationship that we have a binding constraint. And then we can start, well, start where we want to, but 1 and 2 can be combined because we have here x, y, z and here y, x, z, so we can subtract, and then we get that lambda x squared is lambda y squared. Since lambda is bigger than 0, from this lambda is bigger than 0, from here we get here that y is x. then we can put y as x, then we can continue from there. We can put y as x back in 1, for example, and then it splits up in two cases, a case A and a case B, so you can do that. So that was, just say that was B3. Go to B4, move it, so that follows the nodes A and B. C. Oh, it's quite, what are we supposed to do? B. So it's quite this follows the nodes. Let's first, oh, I don't have anything left, so any space left this way, so let me minimize it a bit more. It's not very desirable, but see what I can do. Why does it do that? I have now minimized it too much. Plus, yes, no. What is irritating? That's it. Oh no, not quite. Oh. Now I have some space left. Well, I'm not sure if this is going to be. Well, I'm supposed to give tips anyway. Tip, tip, tip. So here, no. I'm trying to find where I am because it's blocking it, of course. So that's a bit lower. So this one can, yes. So let's see. What do we have to do? Let's take that out. Why is it doing that? That's it. Yes. So what we're doing, we have a firm revenue depends on the rate of production Y and the advertising expenditure, so the cost A according to a revenue R, which is some power loss. It's kind of like a Cobb-Douglas production law. Cost of production is Y, so the profit is R minus C. So that's the R minus C minus A, because of course the advertising cost as well. So cost of production and the cost of advertising both have to be subtracted. So that gives you the product. We have constraints Y is bigger than 0. So the production and advertised costs are bigger than 0. So we need to have a Kuhn-Tucker Lagrangian as said. So that's for A. B4A. Well, now argue why y a and lambda. So because y and lambda are the unknowns. Well, that should be pi minus lambda, and we want the profit to be bigger than 1, so we want here 1 minus pi. And pi of a comma y, or y comma a, is 3y1/6 a to the power 1/6 minus y minus a. So you just have to substitute that in there and substitute that in there. Then you write down the KT relations, which are, what is it, y, dl bar dy is 0. Rearranging gives you the first relationship which is given, so be a bit careful. You have to rearrange it, but it's just this one. Then a dl bar dA is 0. That gives you the second relation, and the third relationship will be this one is 0. Now you need to write down the a is bigger or equal than 0, y is bigger or equal than 0, lambda is bigger than or equal than 0, plus the other relationship and the other relationship, right? There are three more relations, so 3 more, so you can figure that out yourself. Now you have to since so the solutions, once you've done that, is pi needs to be bigger than 1, and we have pi there, pi is bigger than 1, and that means figured it out that y needs to be bigger than 0 and a needs to be bigger than 0. So figure out that because y is 0 and a is 0 leads to violations. Check that. Now from that first relationship, which is written down there, you can see that if lambda is 0, that 1 is 0. So that 1, so lambda 0 is not possible. So that means that lambda is bigger than 0. That means the constraint is binding. And if the constraint is binding, then we can rearrange the first 2 relationships to find that, so use 1 and 2. Well, 1 and 2, I haven't labeled it, but those are the first 2 relationships. So I give you that y is a, and then it's a bit of arithmetic. So in B2B, we have a different strategy. We're not constraining our or rather pi. Well, we're not constraining R via pi. So it's just a regular case. So we maximize pi of y comma a. So it's a unconstrained problem. Which you're familiar with. And then the problem unfolds itself. So this is a standard case. In this case also, y is a at some point. Did I say B2? That must of course be B4B. Did I say B2 here? No, B4A. B4B. So A1 you start considering the complementary slackness conditions, so the three ones in turn, to figure out which lambdas are bigger than 0. There will be 2 lambdas bigger than 0. The sketch is self-evident. In A2A, you're supposed to do Cohn-Tucker theory. A, it's best to start with the main constraint, so either then lambda is 0 or lambda is bigger than 0, then the constraint is binding. For the lambda is bigger than 0 case, you consider it will only you have to figure out whether x or y can be 0, but ultimately only x bigger than 0 and y bigger than 0 are allowed. Then you re-express x comma y, for example, in terms of lambda. Solve for lambda using the constraint, solve for lambda, and then you have found x and y, and then you can and then you have found x, y, and lambda. So for A to B, that is A2. That's A2. Let's say A to B. Where is a linear problem again? So that should actually unfold. Linear problem with a nice sketch again. So that should work out all right.